Hi and welcome. This time around we need to make an XY platform for laser welding. I'm still working for the same company that I usually consult for, and they want to make an XY movable table that will let you position a part to be laser welded. The problem is that the accuracies required exceed common layouts like this. So this is sort of an H-rail system where you have two motors running on the same rail for one axis and one rail being one motor for the other axis. But the way they decided to set up the positioning for this is to use nylon rollers on extruded aluminum, and so the repeatability and accuracy is not great. There is a fair amount of play in this, and if you need, within 5,000ths repeatability, this probably isn't going to be your best solution, even though all you're holding is the part and there's no real force being applied to the part during welding, so that's not a problem. But this kind of gantry setup, H-gantry, or I don't know, H-rail setup, I'm not sure what they call this, is not ideal. It's just not stiff enough and repeatable enough. So we're going for a different design. Instead, we're going to use two of these guys. These have linear rails on the bottom with a ball screw positioning system, so they're reasonably accurate. They have fairly beefy stepper motors, and they're going to be mounted one on top of the other. So I'm going to need to find the center of gravity of one of these guys, and we're going to mount it on top of the other unit like this. So position back and forth this way, and then this part here will move back and forth to hold the final plate that holds the part on it that they're going to be welding. I would have liked to have a shielded version of this. This was sort of a test setup for a very limited run of parts because all the welding spatter and everything is going to get on these ball screws, which is not a good idea at all. They do make enclosed versions of this, but time was of the essence, so there was no way to wait for delivery on the other parts. I think they're going to order those as well. I'm not sure. Again, there's a limited run of parts. I think they've got to do like 20 parts as a proof of concept before they get the contract. Then if they get the contract, then they'll have to, get the appropriate shielded ball screw solution, because I don't think this one's going to do well with weld spatter getting all over the place. And believe it or not, lasers do spatter quite a bit of material about. You wouldn't think so, but they vaporize in the cloud and it recondenses and then settles out. And if you notice around a laser welding bench, well, you probably haven't been around one, but there's like a black film all over the place, and that's little condensed particles of material fallen and settled back on the ground. So anyways, we need to make a plate that's going to go mounting it. Oh, and by the way, all of this, besides the XY positioning, all of this fits inside of an enclosure that first you pump down to a vacuum, and then you purge with a neutral gas like nitrogen or argon. I think they're using nitrogen in this particular case. And the entrance to this chamber, this is a pretty big chamber. I don't have any video of it right now, but maybe I can get some before this video's over. The entrance, it has an oven in there where they can cook off all the moisture and then pump that down. They have a vacuum pump in that chamber. And then once all the moisture is removed and you've pumped it down to very close to vacuum, then you open the chamber into the environment where this will be, and they've got gloves where you can grab the parts out of, and you will then position the part, flood the chamber with dry nitrogen, I think is what it's going to be, or maybe it's going to be argon, I don't know, and then laser seal the part, and that way it'll be hermetically sealed in a dry environment. It's for encapsulating something that can't afford to get corrosion over time. So the bottom one of these guys is going to be mounted on a plate that fits on another plate that's pre-drilled, and that way we can make adjustments and move things around. So first up, we need to get a big piece of say 1/2-inch tooling plate for the base of this unit. Then we need to make the adapter piece that is going to go on here that will hold this guy in place, and then we made to make the adapter plate that holds the tooling plate that's going to sit up here that will hold the parts themselves. Oh, and then we've got to wire it all up and get the controller. We've got a general open source controller This is the one they chose to use. They picked this one out. I mean, there was some input from me, but they'd used this one before. So they're going to use this controller, motion controller with drivers, stepper drivers built in to control this unit. So a lot of times steppers go first to a driver module, and then the driver module attaches to the controller. That way all the high current, high voltage switching is done by a dedicated module that can get adequate cooling and whatnot. This is an all-in-one solution, doesn't require that. A step better of improvement. So these are just plain stepper motors. Now with a stepper motor, you tell it, you feed it a pulse and it should advance one stop, right? But let's say there's too much force on it and it can't. It seizes rather than advancing a spot. Well, you're no longer where you thought you were. And every time you advance and you tell it to advance, but it doesn't actually advance, you're farther out of position. So a better version of this is a stepper motor with another module on back with an optical rotary encoder that will let you know whether you actually advanced what you thought you told it to advance. So that's important, and that's a better version. And when that whole thing is involved in feedback, that's called a servo loop. Now, I'm not sure if there's a difference between a dedicated servo and a stepper with an optical encoder with circuitry that provides that feedback. I think they're pretty much the same, but there might be some technical differences. This is not my area of specialty, so I'm not entirely certain. Got some material for the base plate here. It's a cut-off, so it's a lot cheaper than having a piece cut for you. The place I buy it from probably saves you a couple bucks a pound. I'm also using that spacer back here to keep the saw blade back so more of the material can be on the table for these wide pieces. You've got a clamp that just presses on the back that holds it in place so that the saw blade can't go back. And this space is off the table. Again, at some point I should do some sort of threaded thing where you could just adjust it really quickly. That'd be handy. But in any case, yeah, we're just going to cut this guy off here. And we will take it over to the mill where we use another tool I just made. This might be a total fail, but I'm going to let you ride on top of the part I'm cutting. It seems like a really bad idea, so of course we're going to try it. So there's the problem. I've run up against the column. That is one of the problems with this kind of saw. So now I'm going to have to flip the part around and cut from the other side. Remember how I talked about squaring up large pieces of tooling plate was problematic? And that's why I made this fence system. Well, I'm going to use it already. I'm going to actually mount this on the other side, but you get the drift. You line this up. It's got a little bit of slop here, and you line it up with the T-slots. I use 3 T-nuts in it because it actually has mounting points to hold the hold-down clamps built into it, which is really nice and convenient. And you can have up to 3 of the clamps there. As a matter of fact, I think I want to use the bottom 2. Well, I guess I'll play it by ear for now. I got to see how this is going to hold when I clamp it, but I've got to dial it in. So that's one thing that definitely needs to happen. And then you just pick one side that you think's your square side, put it up against the fence after you've dialed that in, and then you run this length. And then if you have the range, you could do this side, you could do 2 sides, and you know they'd be square. But if not, you do this length, then you could rotate 90, do this side, then flip it 180, do the other side, and then finally do the back side after pressing up against the fence. And you've got a pretty square piece of plate. Now this doesn't have to be super precise, but my saw cut side is definitely not great. So we need to fix that for sure. So let me get this set up, dial that in, and we'll move on to the next step. I know it's the opposite side, but I got this guy dialed in within a couple tenths along the entire length here, and then just snug down all 3 T-slots. And now you can, T-bolts, now you can see why you want 3. If you're actually going to lever off of this with a clamp system, then you want, you know, as much support in your T-slots as possible, because I've heard of them breaking out because it's just cast iron. So anyways, we're ready to move on and start doing some milling. All right, I got this guy clamped down, and I'm only going to do it with, try it with 2 clamps. I think it's going to be adequate. It feels super tight. I've got 1-inch spacer blocks under here that I buy some 1-inch tooling plate and cut it off into pieces. I did check for burrs first with some precision ground flat stones, but it feels super tight up against the fence and these 2 hold points here. And all I am going to be doing is cutting along one edge pretty lightly, not taking off a lot of material. So I think that should be adequate. And the end mill I'm going to use is a zircon nitride coated end mill that you can tell I exploded at some point in time. Happens to me all too often. If I was in business for myself, I'd be in a lot of trouble because these are like 50, 60 bucks a piece. But it's fine for edge milling, which is what we're going to do. So that's why I didn't get rid of it, because it's still razor sharp on the edge milling. So we're going to pop this guy in here and just go along the edge and square this guy up. Going to take a 25,000th depth of cut. 1,000 RPM. I don't think this should be any problem at all. Almost no vibration, which is great. This will give me my first square side, and then we'll put this side here that we're just cutting now up against the fence and get a perpendicular side. Doing big piece of tooling plate like this can be challenging if you want some kind of precision. For the really long direction, I decided to go with a 3rd clamp at the end here because it was springing up just a little bit and I didn't want any vibration, so now it's nice and solid. Now we can run the length. I probably don't need 2 clamps at this end anymore, but I'm just going to use all 3. Why not? Because we're already there. So next run, this is a square edge. That's the side I just squared. I use the precision ground flat stones to clean any burrs off that side. By the way, they work fine on aluminum. You just got to clean them. And I'll show you how to clean them later using WD-40 and a piece of cardboard. It's surprising how well it works. So now we're going to run this end down here. When I'm done, I'm going to flip it over and just do the opposite side, which will make both of these perpendicular to that side. And then finally I'll rotate it and do this last side, and we should have a nice square part, 2 dimensions. So this one's just going to be cut, a straight cut, and the other side will actually do it to dimension. I don't have a specific dimension this needs to be. And that mess there is what happens when you accidentally put your mill in reverse. I don't know why it was even displacing the material. Thank God it was only 25 thousandths. Of course, now I've got stuff all gummed up on the cutter. So we're going to try and clean that off. I couldn't figure out why it sounded strange, and now I know why. That was a total novice move right there. Hopefully we can get all that welded aluminum off, otherwise we're going to have to find another way to clean this cutter, but it is cutting pretty well. So I used the precision ground flat stones to take off high spots, which there was a burr created at the end here by me trying to displace the material with the mill running backwards. And you can see it's just hitting high spots on the top. And I'm doing this for my own knowledge and education because this project does not actually require super accuracy, especially in this plate, not at all. You can see all the welded on mess there. I don't know that that's coming off, but I'm gonna take a 50,000th bite here. Hopefully we can clean that off. I might have just totally hosed this cutter. Listen to the sound it's making now. Listen to the sound when I spray. If you ever wondered if lubricant makes a difference, you can hear right there. So remember when I said I got this flat square within a few tenths between here and here, so 4 inches or something like that? I didn't go all the way to the end. Well, that was a mistake. I should have been more precise about it, because by the time you travel 20 inches, it was off by 7 or 12 thousandths. So what I ended up doing was loosening, keeping this tight, loosening these two, Finding out the amount that this was off down at this end down here. This was obviously sticking this way into the cutter because it removed extra material down here, not as much material down here. So I moved this, I tapped this end of it, which caused this to rotate just enough to make up for that 12 thousandths, and I got it within 2 thousandths from end to end. So that's not terrible, considering I didn't need anything like that kind of precision. I just wanted to see if I could. We were able to get it a little better. So next time, got to put a square against this and then run the x-axis to make sure it's square, not just along this length, because that's not adequate. It's too short a distance. By the time you're off by a little bit of an angle, it magnifies by a ton down here. Also, on one of my passes, I got a chip in here, and that pushed it out enough that it was actually off by like 30 thousandths. Fortunately, I caught that before I committed and was able to fix it. Remember when I told you I'd show you how to clean these? Well, they got some aluminum schmutz in there that kind of gets buried in there, and this side's even worse. So all the trick is, you just take a piece of cardboard, wet it down with some WD-40, and just rub it. So you can see it's already much better. The bigger chunks are harder to remove, but you can see all that film that was on there is now gone. And you just keep going. Like this one, you can see the film on there. I don't know, maybe you can get the angle. It's like an aluminum film. If you're asking me the reasoning behind how this works, I can't tell you that, but I can tell you that it takes off most of that film. So some of these particles stayed. I guess you could use a brush maybe with that, I'm not sure. But there was that film, that glaze over it, and that all came off. And you can actually see it on the paper. I don't know if you can, but it's pretty obvious on the paper. Next up, we're going to drill and tap the mounting holes. Next up, we got to get the mounting holes for this guy. And part of my problem is that this was designed to be mounted from the bottom, which, you know, you could drill through the bottom of the plate and screw into the tapped holes. These are M4, and that would be fine, except I have an issue with that, and that is this is going to be bolted down inside a controlled atmosphere chamber. That's probably the best name for it. It's not exactly a vacuum chamber. It's designed for like an inert atmosphere like nitrogen or argon. In any case, that environment makes it problematic to unscrew this, flip it over, move the whole assembly over, because there's two positions where they may need to use this. So I guess ultimately I need to mount this from the top. So there's a couple ways I could mount it, and one is I could use these side channel pieces here and have something that slips in there and tightens down. That would work. Or I could just bore these holes out and drill and tap them for some size that would, you know, fit through there. It has a linear rail, so that shouldn't be a problem. I'm not sure about what my solution is at this point in time. I kind of leaning a little bit towards the side mount, but that's kind of a pain. So I got to think about this, because this is not designed. This is something I'm doing. This has two positions where they're going to use it commonly, I think, here and roughly here. And I might do an interim spot just because what they need to do is buy longer ball screws so that there's more range, because the laser, for one of the scenarios, the laser that sits right here is a long tube on a that's connected by a fiber, and they want to rotate it at 45 degrees because they want to do the weld at 45 degrees. So you can see already that anything you have mounted up here needs to be all the way over here for the laser to hit it. But other times the laser is going to be straight down, in which case it needs to be here. The laser is centered on this plate. So I got to think about this. I think I figured out the mounting scheme, so now we just need to implement it. I didn't do full drawings for this whole thing, so I'm sort of designing it as I go. Prototype, this is typical prototype work I would expect. So this is a tap drill for 1/4 20. Just going to countersink these before I tap them. All right, I think we're done with this guy. I need to chamfer these edges because they're all sharp. I flattened off this corner here to let me know that this is my reference corner, and that'll be for future projects. I know I've shown this before. I'm going to use the tapping head, set it for 1/4 20. Well, you set it for 1/4, and depth is 22, but that doesn't matter because you can preset depth, and we're just going to tap each one of these holes. I'm going to use some anchor lube as the lubricant.